Kylo Limit Loren, talking to you about horizontal asymptotes and limits at infinity. What's the dark side's favorite potato snack? Vader Tots!
First thing we're going to talk about is a horizontal asymptote. That's the line y is equal to L toward which a function f of x approaches infinitesimally closely as x approaches infinity or negative infinity, but never reaches the line as x increases or decreases without bound. So a horizontal asymptote, that is going to be a horizontal line. That's why it's y is equal to L, y equals some number. That's a horizontal line toward which a function f of x approaches infinitesimally closely. The function gets very, 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 very close. So in this case, the function f of x approaches as x approaches infinity. The function approaches 0, right? It gets very, 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 very close to 0, infinitesimally close to 0, but it never quite reaches that line. It also, as x approaches negative infinity, approaches 0 as well. Now, when we're talking about limits at infinity, that's the limit of a function as x approaches infinity or negative infinity. So here you can see that the limit as x approaches negative infinity, so as your x value approaches negative infinity, your function, your f of x, approaches 2, right? That line y is equal to 2. That's your horizontal asymptote. Same thing over here. The limit as x approaches positive infinity, as your x value increases towards positive infinity, your function gets closer and closer. Your f of x, your y value, gets closer and closer to 2. In indeterminate form is any of the 7 undefined expressions: 0 over 0, infinity over infinity, 0 times infinity, infinity minus infinity, infinity to the 0 power, 0 to the 0 power, and 1 to infinity, that a mathematical function may assume by formal substitution. So anytime we get an indeterminate form like infinity over infinity, you're going to have to go back and try to simplify it some other way, or just try to recognize what the limit is going to be. Now let's get more in depth about horizontal asymptotes. So the line y equals L is a horizontal asymptote of the graph of f when the limit as x approaches negative infinity of f of x equals L, or the limit as x approaches positive infinity of f of x equals L. And if we look at this example down here, you can see that as your x approaches negative infinity, your f of x, or your function, gets closer and closer and closer. That y value gets closer and closer and closer to 2, but it never quite gets there. Therefore, your graph is going to have a horizontal asymptote at y is equal to 2, because the limit as x approaches negative infinity of f of x equals 2. Same thing on the positive x-axis. If you take the limit as x approaches positive infinity of your function here, you can see that it gets closer and closer and closer to 2, but it never quite gets there. Therefore, the limit as x approaches negative infinity of f of x equals 2, and you have a horizontal asymptote at y is equal to 2. That's what that means. Now, properties of limits at infinity. So let f and g be functions such that the limit as x approaches infinity of f of x and the limit as x approaches infinity of g of x exist. Then the sum or difference rule says the limit as x approaches positive infinity of f of x plus or minus g of x is equal to the limit as x approaches infinity of f of x plus or minus the limit as x approaches infinity of g of x. And the product rule still holds up as well. The limit as x approaches infinity of f of x times g of x is equal to the limit as x approaches infinity of f of x times the limit as x approaches infinity of g of x. These rules you saw when we were talking about limits at first, and they still hold up when you take the limit as x approaches positive or negative infinity. Now, we're talking about finding limits at positive and negative infinity of rational functions, okay? And remember, a rational function is just when you have a polynomial in the numerator and denominator. So, it says if the degree of the numerator is less than the degree of the denominator, that means your m exponent is less than your n exponent, then the limit of the rational function is 0. So here, if we have the limit as x approaches positive infinity of a times x to the m over b times x to the n, where m is less than n, that means your limit is going to be equal to 0, whether it's positive or negative infinity. As long as you know that your degree in the numerator is less than your degree in the denominator, your limit as x approaches infinity or negative infinity is going to equal 0. And that's because, if you think about it, when you put infinity in for x here and here, this number down here, because it has a higher degree, higher exponent, is going to become a bigger number than this one up here. This is going to be a really, really big number, and this is going to be a smaller number. So if you have a small number over a really large number, as it approaches infinity, right, it becomes 0. That's why your limit as x approaches infinity or negative infinity of x to the m over x to the n, when m is less than n, is going to equal 0. The second case would be if the degree of the numerator is equal to the degree of the denominator, where m is equal to n, then the limits of the rational function is equal to the ratio of the leading coefficients. So here we have x to the m over x to the n, where m and n are equal to one another. So the degree in the numerator is equal to the degree of the denominator. If we're taking the limit as x approaches infinity of that, what we can then do is to figure out the limit, we just look at the ratio of the leading coefficients. So this limit is equal to a over b. Just as if you were to do the limit as x approaches negative infinity, same thing. You would get a over b when these two exponents are the same. If the degree of the numerator is greater than the degree of the denominator, so m in this case is greater than n, then the limits of the rational function approaches infinity or negative infinity. So if you're taking the limit as x approaches infinity of a times x to the m over b times x to the n, and m is bigger than n, let's say x to the third up here and x to the first or x to the second down here. When you plug infinity in for x here and here, you end up getting a really, really, really big number over a smaller number. And as you approach infinity, this increases without bound, and this can't keep up. Therefore, you end up getting either infinity or negative infinity. And you have to check. Anytime you have a higher degree in the numerator than you do in the denominator, you have to check by plugging in values as you approach whatever this is. You need to plug those in and see if it approaches infinity or negative infinity. Now let's talk about finding limits at positive and negative infinity of transcendental functions. And remember, those are like trigonometric functions or exponential functions or log functions. First, what I want to do is just off the record tell you that 1 over infinity you need to think of as 0. And it makes sense, right? Because 1 over infinity, this number is enormous. And 1 over that number is going to get you 0.000000, continuing forever until you get to 1, but you never get there because this is infinity. So 1 over infinity you need to think of as 0. Just as 1 over 0 you need to think of as positive or negative infinity. Remember, we were finding vertical asymptotes, and our limits would sometimes come out to numbers like this. And what you can then do, instead of writing the limit does not exist, you can write the limit is going to equal positive or negative infinity. You just need to plug in values and see which one it is. Now, you can use the same mode of thought for transcendental functions. So for example, we have the limit as x approaches infinity of sine of x over x. If I were to plug in infinity here, sine is just a number where the y values bounce between x and y. Sine is always going to be somewhere between 1 and negative 1. However, x, that number is going to, as x approaches infinity, become super, super, super big. So this is just going to be somewhere between 1 and negative 1 forever, whereas this is going to become enormous. So we're going to have a small number over a really large number. Therefore, if we have a small number over a large number, we can always think about that as 0. Okay, so the limit as x approaches infinity of a really small number over a huge number is going to equal 0. And you can confirm that with your graph. You see that if you have sine of x over x, as x approaches infinity, this little bouncing back and forth gets smaller and smaller and smaller, and it approaches 0. Now the limit as x approaches infinity of e to the negative x, this is a little different, but it's kind of the same. So e to the negative x is the same as 1 over e to the x. So I have 1 over e to the x, but as x approaches infinity, I plug in infinity here, and this number gets enormous. It becomes infinity. So I have 1 over infinity. And we said when you have a small number over a really large number, like 1 over infinity, the limit as x approaches infinity is going to equal 0. And you can confirm that with your graph. The limit as x approaches infinity of e to the negative x, your y value just keeps getting closer and closer and closer to 0, but never quite gets there. The limit as x approaches negative infinity of e to the x, you can think about in the exact same way. Because you are plugging in negative infinity here, this number is going to be negative. It's going to be a huge negative number, which means we can think about it as 1 over e to the infinity. And we just said 1 over e to the infinity is just a small number over a huge number, a really large number. Therefore, the limit as x approaches negative infinity of e to the x is going to equal 0. And you can confirm that with your graph. As x approaches negative infinity, your y value of your graph gets closer and closer and closer to 0.
I brought your teacher out here to say hello.
Hey everybody, how's it going?
No more talking! Example time.
Now, example 1, we're finding the limit. If you remember your properties of limits, you know that you could take the limit as x approaches infinity of this first part minus the limit as x approaches infinity of this second part. So let's do that. We break it up. And the limit as x approaches anything of a constant is just equal to that constant. So the limit as x approaches infinity of 5 is just going to equal 5. But over here, it's a little different, right? If we think about the degree of our numerator versus the degree of our denominator, the degree of the numerator is basically x to the 0 power. The degree of the denominator, that's x squared, so that would be 2. So the numerator has a smaller degree than the denominator. Because of that, if we were to plug in infinity here, we would get 2 over infinity squared, which is going to be a small number over a really large number, which means this limit is going to equal 0. We just said this limit over here equals 5, therefore 5 minus 0 just gives you a limit of 5. And you can confirm that with your graphing calculator. As x approaches positive infinity, your y value of your function gets closer and closer and closer to 5. For part B, we're taking the limit as x approaches infinity of 3 over e to the x. Now, again, you're plugging in this infinity for x, so you're getting 3 over e to the infinity power, which is going to equal a huge number. So you're going to get a really small number over a really large number. Anytime that happens, you're going to end up getting a limit that as x approaches infinity equals 0. You can confirm that with your graph here too. If you were to graph 3 over e to the x, you could see that as x approaches infinity, your y values get closer and closer and closer to 0. Now, based on the properties of limits, we know that we could take the limit of each of these terms here. When we do that, we can see that this is x to the first over 5 and technically times x to the 0 power. So the higher degree is in the numerator. And because of that, when you take the limit as x approaches negative infinity, this is going to approach negative infinity actually. And then over here, if you were to plug in this negative infinity down here, your higher degree is in the denominator. Therefore, this is going to approach 0. And when you have negative infinity minus 0, that's just negative infinity. And if we were to confirm that with your graphing calculator, you could see that there is no horizontal asymptote between these two parts of the function. Therefore, the limit as x approaches negative infinity, this just keeps going down, so it would be negative infinity. So for part B, you can use your properties of limits and actually take this 2/3 and move it out front, and then you have 2/3 times the limit as x approaches negative infinity of e to the x. And we talked about this a little earlier. When you take the limit as x approaches negative infinity of e to the x, e to the negative infinity is approximately equal to 1 over e to the infinity. And when you have e to the infinity, that's a really big number. So you have a small number over a huge number, that's approximately equal to 0. And 0 times 2/3 is equal to 0. You can confirm this with your graphing calc. As x approaches negative infinity, you can see that your y value of your function gets closer and closer and closer to 0. So example 2 says find the limit, and we're taking the limit as x approaches negative infinity of this rational function. Now, as you can see, this is x to the first up here and x to the first down here. Because the numerator and denominator have the same degree, what we're going to do in order to find our limit is we are going to take the ratio of the leading coefficients. And the leading coefficients here are going to be 2 in the numerator and 1 in the denominator. So 2 over 1 is going to give you a limit of 2. Now, the reason this works is because if you plug in negative infinity up here, 2 times negative infinity is 2 times negative infinity. And then minus 1, this doesn't really do anything to infinity or negative infinity. So this you can kind of just disregard. Whereas down here, you have negative infinity plus 1. And again, negative infinity plus 1, the plus 1 doesn't even matter because this is negative infinity. So we end up having 2 times negative infinity over negative infinity. And then negative infinity over negative infinity just turned to 1. So you end up getting 2 times 1, which ends up being 2. And that's why that works. Confirm that with your graph. Here, if you were to graph that, you can see as x approaches negative infinity, your function or y value keeps approaching 2, and that is why you have a horizontal asymptote at y is equal to 2 and a limit as x approaches negative infinity of 2. So for part B, you can see the limit as x approaches infinity of this rational function. What I would do is rewrite the numerator and denominator so that they're both in standard form, by which I mean they both go from greatest degree to least degree. Now we could see what the degree of the numerator is. That would be x to the first, so 1. And the degree of the denominator is going to be 2. Because the degree of the numerator is less than the degree of the denominator, you know that this rational function is going to approach 0 as x approaches infinity. That's because up here, when you plug in infinity, you're going to get a smaller number than you would down here, because infinity squared is going to end up way more massive than just infinity up here. So this whole thing, because you have a smaller degree in the numerator than you do in the denominator, is going to approach 0. And you can tell that from your graph. As x approaches infinity, your function, your y value, is going to get closer and closer and closer to 0.
You try.
Okay, so up here you see that your degree in the numerator is 2, degree in the denominator is 1, x to the first. Since the degree in the numerator is greater than the degree in the denominator, you're going to have a really large number up here and a really small number down here. So your limit then, as x approaches infinity, is going to equal either infinity or negative infinity. To figure out which one it is, you then have to plug in a really big number. So I just plugged in 100, you could plug in 1,000, 10,000, whatever you want for x, and just see what you get. So if I plug in 100 up here and square that and times it by 2 and then divide that by 101, I end up getting a really large positive number. Therefore, my limit as x approaches infinity of this rational function is going to be positive infinity. You can confirm that with your graph and see that as x approaches infinity, this function just increases without bound. Down here, the limit as x approaches infinity of this rational function, again, rewrite it so it's in standard form in the numerator and denominator. You can see that they both now have a degree of 1. So because they are the same degree, you then look at the leading coefficients, and your limit is going to be equal to the leading coefficients. So this is going to be equal to, since this becomes just infinity over infinity, it's going to be negative 3/4 times 1, which is just negative 3/4. Now I can confirm that with my graph. As x approaches infinity, you can see that your y value of your function is going to get closer and closer and closer to negative 3/4, because that's your limit. Example 3 says find the limit by completing a table, graphing the function, and then find it analytically. So first thing we're going to do is complete this table. You can see that we have the limit as x approaches infinity of this function. So I'm going to pick x values that approach infinity. So I keep plugging in these x values. 1 when I plug in is actually undefined, then 10, 100, 1,000, 10,000, 100,000, and then 1,000,000. And you can see that as x approaches infinity, it looks like your y value, your f of x, approaches 1, right? Gets closer and closer to 1. So it looks like from the table that the limit as x approaches infinity is going to equal 1. If I were to look at the graph, you can see as x approaches infinity, your y value of your function gets closer and closer and closer to 1. So again, graphically, it looks like the limit as x approaches infinity of this function also equals 1. If I were to do it analytically, I could see that the limit as x approaches infinity of x over rad x squared minus 1, the degree in the numerator is actually 1, while as the degree in the denominator, while you might think it's 2, you're taking the square root of that. So technically it's 1, which means they are the same. Because it's the same degree in the numerator that it is in the denominator, you go by the leading coefficients, which in this case is just 1 over 1, which is 1. That's how that works.
You try.
So this time we're taking the limit as x approaches negative infinity of this rational function, and I'm going to pick x values that approach negative infinity. Now when I plug those in, I end up getting the corresponding y values, or f of x values, and you can see that it looks like your f of x, your y values, increase without bound, which means that the limit as x approaches negative infinity of this function should be equal to infinity. Let's check with our graph, and you can see that as x approaches negative infinity, your f of x or y value keeps going up. Therefore, it looks like graphically also the limit as x approaches negative infinity equals infinity. Lastly, we can think about this analytically, and if you were to look at the numerator, it has a degree of 2, whereas the denominator, you might think has a degree of 2, but you're taking the square root, so it actually has a degree of 1. Because the degree in the numerator is greater than that of the denominator, this is going to approach either positive or negative infinity, so you just have to plug in values and see which one it is, and it looks like it's actually going to approach positive infinity. Now example 4, we're again finding the limit, and this time it's as x approaches negative infinity of cosine of 1 over x. Now if I were to plug in this negative infinity down here, what happens is 1 over negative infinity, this becomes a really big number, and 1 over a really big number is about equal to 0. So we get cosine of 0, which is just 1. And you confirm that with your graph. As x approaches negative infinity, your y value of your function gets closer and closer and closer to 1. Now for part B, we're taking the limit as x approaches infinity of this log right here. First, simplify this a little bit just to make it easier on yourself. 10 to the negative x over 2 is the same as 1 over 10 to the x over 2 power. Now if we were to plug in this infinity down here, 10 to the infinity over 2 becomes a huge number, right? 10 to the infinity divided by 2. Even infinity divided by 2 is still an enormous number, so 10 to that power is going to be huge. And 1 over that huge number is going to equal 0. And then you have 5 over 5 minus 0, which is just 5 over 5, which is 1. And log of 1, we know, is 0. And you can tell by this graph that as x approaches infinity, your y value of your function gets closer and closer and closer to 0. Now, example 5, we have the limit as x approaches infinity of 1 over 1 plus e to the negative x. And what you can actually do then is take the limit as x approaches infinity of each of these parts of the function. Now, the limit as x approaches infinity of 1 is just 1. The limit as x approaches infinity of 1, we said, is 1. And the limit as x approaches infinity of e to the negative x, we said, is 0. Because e to the negative x is 1 over e to the x. And if you plug in infinity for x, you get 1 over a huge number, which is just 0. Now, this becomes 1 over 1, which is just equal to 1. Confirm that with your graph. As x approaches infinity, your y value of your graph gets closer and closer and closer to 1. Now for part B, we have the limit as x approaches infinity of 1 minus cosine of x over x. If I were to plug in infinity for x here, cosine of infinity, cosine is always going to bounce back and forth between 1 and negative 1. So the biggest this numerator is ever going to get is 2, right? If I get 1 minus negative 1, then I'm going to get 2. The smallest it'll ever get is 0. So what I know is that this numerator is always going to be small. The denominator, however, since x approaches infinity, this is going to be infinity, which is going to be huge. Okay, so I have a small number over a big number, which means as x approaches infinity, this is going to turn into 0. And you can see from your graph that as x approaches infinity, so as you get farther down on the x-axis, your graph, your y value gets closer and closer and closer to 0.
Luke is fat and ugly. You try.
So for this one, again, if we were to plug in infinity down here, 1 over infinity, we said is basically 0. So sine of 0, we then know is 0. If you were to graph that, you could see that as x approaches infinity, the y value of your graph, your function, is going to get closer and closer and closer to 0. Now for part B, we're taking the limit as x approaches negative infinity of 1 over 1 plus e to the negative x. Now if we were to plug in negative infinity here for x, this will technically be 1 over 1 plus e to the positive infinity. And e to the positive infinity is going to be an enormous number. Plus 1 doesn't really matter, but this is going to be a huge number. So we get 1 over a huge number, a small number over a really large number. That's going to equal 0. You can see from your graph that as x approaches negative infinity, your graph, your function, is going to get closer and closer and closer to 0. Now example 6 says find the limit by completing the table, graphing the function, and then find it analytically. So first thing we're going to do is plug in the given values in the table, right? We have the limit as x approaches infinity, so I'm going to pick x values that approach infinity. I plug those in and get the corresponding y values that go with them. And I can see that the f of x, or the y values, increase and keep increasing without bound. Because of that, I can see that the limit as x approaches infinity of this function is going to equal infinity. Now, just by looking at the graph as x approaches infinity, it looks like the graph kind of rounds off here, but you have a really small window right here. So if you were to increase your window size, you could see that the graph actually keeps increasing without bound. Therefore, the limit as x approaches infinity of this function looks like it's going to be equal to infinity. Analytically speaking, you can determine that the numerator has a degree of 1, whereas the denominator, while it might look like it has a degree of 2, because of this 1/3 exponent right here, it actually has a degree of 2/3. And that means that the degree of the numerator is greater than the degree of the denominator. Because of that, you're going to have a really large number over a smaller number. This number is going to increase, and get really big. This number also increases, but at a smaller rate. So you're going to get a number that's really big over a smaller number, which means this is going to be equal to either infinity or negative infinity. And to figure that out, you have to plug in a value as x approaches infinity. So let's say 100. You can see that it's positive. Therefore, your limit as x approaches infinity of this function is going to be equal to positive infinity. Now, there's two special cases I want to talk about right now. The limit as x approaches infinity of sine of x. If you plug in a number for x here, the sign of that number is either going to be between 1 or -1. So, as x approaches infinity, this sign of x is going to keep bouncing back and forth between a y value of 1 and -1. Because of that, it's not going to have a limit. The limit does not exist. And you can see here that it never approaches anything. It just keeps bouncing between 1 and -1. Similarly, the limit as x approaches infinity here, this number gets really big, whereas this number, remember, bounces back and forth between 1 and -1. So you would think that this would have a limit of infinity or negative infinity. But the problem is this number bounces back and forth between 1 and -1. So while this number gets big, this number makes it go from positive to negative to negative really big, and you never really get a limit, right? It never really approaches either positive or negative infinity. It tends to go both directions. So because of that, it has a limit that does not exist.